Hi 254, welcome to our second video for section 11.9. I want to start out this video with having you look at an example from our textbook, and then we'll talk about what the result gives us graphically. So just a reminder, we've got this alternative curvature formula that we came up with using the cross product of acceleration and velocity, and I'd like you to look at example number 4 that's on page 763 of your textbook. It's a pretty short example. Just give that a quick read before continuing on with the video. Again, a good idea would be to pause this video right now, go look at that example, and then come back and restart continue, I guess, the video. Okay, so go do that now. I'll wait. And you're back, hopefully. Hopefully you've looked at that example number 4 on page 763, and the result that we get from doing the cross product calculation for curvature gives us a curvature function. Again, it's dependent upon t, not arc length this time. Again, remember, we have a different version when it's dependent upon arc length, but this one's a little more free because we don't have to have a curve parameterized by arc length. This one, we can just have t. So what we get is a curvature function here, because of course the curvature of the curve depends upon where you are on the curve, correct? There's places where it's more curved and places where it's less curved. So depending on what value of t you have, where you are on the path, your curvature will be a different number, which is why we see this function notation happening right here, okay? So we see that this was the result for our curvature, and graphically, let's see, where was our graph? Here it is. There it is. This is what we can look at as we're thinking about how curvature comes from the path itself, right? So here's the path from example 4. It was a parabola path, right? Described by t, at squared. I think in this case they've actually chosen an a value of 1, I believe, so that it's t squared. And what we see here is this is the graph of the curvature function, right? So this is the curve that is t kappa, right? So that's actually this function that they're graphing, right? If you plug this into your calculator with a value of 1 for a, you're going to get that blue picture right there, okay? And what's interesting to notice is that as you move along this parabola, it's actually generated in this sort of left to right manner here. They didn't put the orientation arrow, but they should have. And so as you move through the curve here, here on the left, it's straight. There's not much curvature. So down here, we're seeing there's not a lot of the value of the curvature function. The value of kappa is small. It's near 0, right? As we get closer and closer to the vertex of this parabola, the curvature increases because it's getting more and more curved. So what we're seeing is as t progresses here, as t moves from -2 to -1 to 0, the value of the curvature function increases until curvature reaches a maximum where? At the vertex, and that makes sense. That's the most curved part of the parabola, okay? And then after it passes by the vertex of the parabola, it starts to lessen in terms of its curvature and become more linear in this way, in this direction, right? Okay, and that's what we're seeing over here, where the curvature is now decreasing, right, as t moves along, as the particle moves along the path or whatever, okay? So thinking about graphing the curvature function and comparing it to the path is a really interesting way to connect the ideas of what the curvature is telling you about the actual path itself. Excellent. So what I want to do now is move on to our second way to talk about how a curve is changing. And the curvature, what we've already done, tells us how fast a curve turns, right? That's this sort of little note we have right here. But a different thing we can do is use a vector to know which way the curve actually turns, right? Because we know a scalar quantity, this kappa thing, to describe how much it's turning or how quickly it's turning, right? How much it's curvy. That's like this picture right here, right? This value of kappa tells us how much of a curve we have. But what we'd like to do is have a different quantifier, a vector this time, to tell us which way the curve turns, okay? And so what we're going to define is here, this is our new definition, the unit vector. It's a unit vector pointing in the same direction as the derivative of the unit tangent vector with respect to arc length is the principal unit normal vector. So again, remember, whenever you take a vector and you take its derivative, you now have two vectors which are orthogonal to each other, right? So tangent vector, this unit tangent vector, points in the direction of the curve's production, right? Points in the direction the curve is being produced, and now its derivative will be orthogonal to that. So there's one of two choices there, right? Because if we have a path, something like this, right, our unit tangent vector will point something like that as long as this is the orientation. This could be our capital T here, right, if it's length 1, okay? And now the derivative of this T is going to do one of two things. It's going to be orthogonal to T, so which means it can go this way, or it could also go that way, right? We've got some choices, okay? And how we actually define this unit normal vector will tell us which one of the two we actually mean, okay? All right, so let's go to our slides here for a second and get a little bit of a feel for this principal unit normal vector. Here's the actual calculation definition for it, not just how it relates to the derivative of the unit tangent vector, okay? But the principal unit normal vector at a point P on the curve at which we have non-zero curvature, right? We don't want to be a line, okay? Because if it's a line, there's no curvature, which means that the curve is not changing its direction anywhere, right? So we wouldn't have to even talk about this unit normal vector, okay? So how we find it is to compute the following. We do dt ds, that's the derivative, but we want to make it unit, so we divide by the magnitude of that derivative vector, okay? And what's interesting is that we've already seen this magnitude dt ds thing before, right? That's the first definition for curvature that we had, okay? So really this normal vector definition turns into 1 over kappa dt ds, okay? An equivalent formula using chain rule definitions, right, is this one down here, which again does not require parameterization by arc length, but just parameterization according to some variable t, like we usually start with, okay? And so here's our definition for the actual calculation definition for the unit principal unit normal vector, right? So we take dt dt, divide by magnitude dt dt. Of course, that's going to give us a unit vector, and it's the instantaneous rate of change of the unit tangent vector. Yes? And then, of course, you can evaluate that at any point along the curve, any value of t. So let's see what kind of properties this principal unit normal vector has, okay? So R is describing a smooth parameterized curve, right? Smooth just means it doesn't have any like cusps or corners, that kind of thing. It doesn't have any places where the derivative is 0, right, for all the components. We have a unit tangent vector t and a principal unit normal vector n, okay? T and n are orthogonal, like I've already prefaced you with, right? They're orthogonal at all points of the curve. So what that means is that their dot product is going to be 0 because vectors that are orthogonal, their dot product is 0 because dot product uses cosine, okay? The principal unit normal vector points to the inside of the curve in the direction the curve is turning, right? Okay, so now this is how we make a distinction between these two vectors right over here, okay? The default declaration for which one of these two is the principal unit normal vector. Both of these are unit normal vectors, but the principal one is going to be the one that points to the inside of the curve in the direction the curve is turning, which means that this one right here is actually our n, right? This one out here is not, okay, because that one points away from the direction of the curve, right? This n right here is on the inside of the curve, okay, as it's generated from left to right as it is, okay? Excellent. So now let's continue on here and see a little bit of an example here. Notice we've got magnitude 1 vectors here for t and n, okay? And as we move along this path here, we see that the tangent vector points in the direction we're going, right? And the unit normal vector, principal unit normal vector n, is pointing towards the inside, right? It's pointing in the direction of the curve that the curve is about to turn to, right? Okay, so it's moving along about to curve right, so the normal vector is pointing to the right. Now it's moving along, it's about to turn left, it points that way, right? Moving along, about to turn right, points to the right, okay? It's always on the inside of the curve. All right, so this is, by the way, just a little bit of a justification for what you're seeing with the derivative of the tangent vector, right? So to sort of give you a little bit of geometric understanding of why it's actually orthogonal again, right? We see that we have this this t vector, this t plus a little bit vector, right? And then when you think about subtracting them to produce that difference quotient, we're actually going to get this vector right here, which again, as you can see, would be a what? A vector that points towards the inside of the curve, right? Pointing towards the direction of the curve changing. Okay? So at this point, what I'd like you to do is, again, read an example for me before coming back. So let's read example number 6, which is on page 765. At the bottom, it's an example calculating the principal unit normal vector for a helix. Give that a read. It's going to use the parameterized by t version for the principal unit normal vector. Give that a read, and then when we come back, we'll do our last video for this section.